Hello everybody. Some of the important problems. One such problem is semi-empirical mass formula. We had to use it for this particular problem to solve. Using the semi-empirical binding energy formula, calculate the binding energy of calcium 40-20. 40 representing its mass number, 20 representing its atomic number. Okay, and you know about the semi-empirical mass formula. The constants were given here. Using all these constants, we are supposed to calculate the binding energy. Some occasions we are asking binding energy per nucleon also. So binding energy per nucleon means how much is the total binding energy. First we had to determine, divided by the mass number. The mass number is equal to 40. That is binding energy per nucleon, because inside that calcium 40-20, inside this particular nucleus there are 40 number of nucleons, protons and neutrons together. It is called by the name nucleon number. Okay, let us solve this particular problem. Okay, a very easy problem. No, it's not such a very complicated problem. That is, it is easy. So semi-empirical mass formula, what it states, how we are supposed to write. The binding energy is given by E suffix B, or binding energy is equal to AV into A minus AS into A to the power 2 by 3, and don't forget capital A representing the mass number, minus AC atomic number Z minus 1 divided by mass number raised to the power 1 by 3 minus A suffix A into A minus 2Z, that whole square divided by A, plus AP into A to the power minus 3 divided by 4, raised to the power 3 divided by 4 with negative sign. Now let us consider first the concept Z into Z minus 1. This particular factor is approximately equal to, here it is, Z square minus Z, that is minus Z is approximately, compared to that of Z square, Z is said to be very small, therefore it can be possible to neglect. So I will write it here, Z into Z, Z square minus Z. This is approximately equal to Z square only. Otherwise we can take Z square minus Z and you can do the calculation. Okay. Yes. One such idea, that is, another idea is compared to Z, it is 1 is said to be very small, therefore it can be negligibly very small. It can be neglected. Okay, anyhow, Z into Z minus 1 approximately equal to Z square. Now let us have all the calculations one by one here. Then we can have a substitution for this equation number, whatever it may be written as 1 or something. For this equation number 1, we had to do the substitution. Okay, let us take up one by one now here. First idea, AV into A. Let us calculate this. AV value is already given. AV value is already given, 14. Capital A is equal to, here, this is atomic number Z, this is mass number 40. So if you want, I will write that also here. Here Z is equal to 20, A is equal to 40. Mass number and atomic number that I have written. Let us have a substitution here, 14 into 40. Multiply these two, you are going to get 560. In terms of MeV, of course, million electron volt, capital M, million electron volt, capital V. Okay. Similarly, let us calculate AS, A to the power 2 by 3. AS value already given, 13. Substitute that into capital A 40, raised to the power 2 by 3. So 40 raised to the power 2 by 3. Do the calculation. 13 multiplied by 40 raised to the power 2 by 3. The value of that is 11.696. Multiply these two, you are going to get 152.04 MeV. Third idea, that is AC. Third component, AC. Z into Z minus 1, approximately taken as Z square here. Z square divided by A to the power 1 by 3. That is equal to 0.6. This is 0.6 into 20 square. Atomic number, that is 20 square divided by mass number 40 raised to the power 1 by 3. So do the calculation carefully. 0.6, this is 400 divided by 40 raised to the power 1 by 3. The cube root of 40, how much we are going to get? So this is 0.6 into the value of this. Do the calculations properly. Multiplication of these two, 66.686 MeV. Okay. The fourth component. This is the fourth component, A minus 2Z whole square divided by A. That is equal to AA, as it is I will write. A is given, of course, 19 MeV multiplied by 0. Do the calculations as it is, because here 20 multiplied by 2 is equal to 40. 20 multiplied by 2 is equal to 40. So A minus 2Z value is equal to 0. So and hence this value is equal to 0. The last component, AP. A raised to the power minus 3 divided by 4. That is equal to minus 34. Because AP is given as minus 34 here. Okay, substitute that value here. Minus 34 into capital A, mass number 40, raised to the power minus 3 divided by 4. Substitution is finished. Do the calculation. This value is equal to 0.063. Multiply these two, you are going to get minus 2.14 MeV. Approximately, actually it is 137 you are getting. Okay. Now going to the equation number 1. Equation number 1. Substitute all these things in equation number 1. The first part you got it as 560. This is your EB. Binding energy is equal to 560 minus 152.04. The third component is 66.686 with a negative sign. Okay, because all of them, the binding energy, it reduces because of these ideas. So here it is increases because of the volume. Okay, so this is minus 2.137. So substitution is over. Do the calculation. Binding energy is this. Binding energy is equal to how much? So you are going to get whatever you are getting, just you add it, do that. 560, 152.04, 560 plus 152.04, 66.686. Okay, so do the calculation, just addition, subtraction, whatever you are getting, just you have to write it. Approximately you will get 335 point something. You write how much you are getting here. So many MeV. This is total binding energy. Now binding energy per nucleon is equal to how much? Binding energy per nucleon is equal to how much? That is equal to how much you got the total binding energy, means this number, divided by the number of nucleons, how many they are present, that is mass number. So just you do the substitution calculation here. Approximately you are going to get the answer as 8.478 MeV per nucleon. This is the answer. Okay. This is one problem. Second problem. Let me go for this second problem. ASTON'S mass spectrograph. In ASTON'S mass spectrograph, the trace of beryllium-9 is obtained with a potential of 350 volts between the plates. What potential has to be applied if the trace of lithium-7 be formed in the same position for the same magnetic field? Okay, this is the question taken from ASTON'S mass spectrograph. Here beryllium 9 representing the mass number, lithium 7 representing its mass number. Okay. Now the thing is, mass of beryllium, just I will write mass of beryllium, means atomic mass number 9, mass of lithium, I will write that is equal to 7. He says same magnetic field that we are using. Here also same magnetic field that we are using. Here whatever the voltage that we are applying is equal to 350 volts. Here how much is the voltage that we are supposed to apply? Potential, how much that we are supposed to apply. This magnetic field multiplied by the voltage is equal to this mass. So use that condition. Mass is equal to here EMF, or maybe the voltage or potential, how much that we are applying, multiplied by the magnetic field. So use this focusing condition. This is called by the name the focusing condition. So I will use the focusing condition here. So what is that focusing condition? The focusing condition, it says that mass for beryllium divided by the ratio that I am taking up here, mass for lithium. Here I suppose to write E1 corresponding value only, or you can write E. What is that EMF for the lithium here? The cross multiplication that just it is said to be a constant here. Okay, lithium multiplied by beryllium. magnetic field for the beryllium. This is no longer holds good, of course. Divided by EMF for beryllium, magnetic field for lithium. Do the substitution here. This is a focusing condition. Beryllium mass number divided by lithium mass number. The cross multiplication, if you are doing, you are supposed to get the condition. That is a focusing condition. Let us do the calculation here. M suffix Be is equal to 9. M suffix lithium is equal to 7 is equal to, okay, lithium EMF that we are supposed to calculate. Lithium EMF, or maybe I can say voltage, how much that we require, E2. That is to be determined. These two get cancelled because the same magnetic field that we are applying here, divided by EMF whatever we are applying for the beryllium, that is 350. Therefore, E for lithium is equal to 9 by 7 multiplied by 350. You are going to get 450 volts. Okay. Yes, so this is another problem, that is one more problem under ASTON'S mass spectrograph. This is the question. Okay, yes. The distance between the traces corresponding to the masses 12 and 16 in an ASTON'S mass spectrograph is 4.8 centimeter. Calculate the mass of a particle whose trace is at a distance of 8.4 centimeter from the trace of mass 16. Mass 16. Okay. Yes, how we are supposed to start with the solution here now. What is the corresponding solution for this particular problem? Okay, it is an ASTON'S mass spectrograph. ASTON'S mass spectrograph. This is the topic from which it has been selected, this particular problem. Mass numbers are, one is 12, the other one is 16. Distance between the traces is how much? Distance between the traces is equal to this. Distance between the traces is equal to 4.8 centimeter. And the distance, whatever it is said to be happening, that is directly proportional to the mass number. Therefore, x minus 4.8 is directly proportional to another mass number, that is 12. Take the ratio. Just you have to take the ratio. The ratio it's taken as x divided by x minus 4.8 is equal to 16 divided by 12. This implies, calculate this by cross multiplication. 12x is equal to 16 into x minus 4.8. 12x minus 6 is equal to 16x minus 16 multiplied by 4.8. Taken to this side, you will get minus 4x This is negative sign get cancelled. Calculate x is equal to how much? So we got the answer 19.2. X is equal to 19.2. So x is equal to 19.2 here. 19.2 plus or minus whose trace is at a distance of 8.4 centimeter plus or minus 8.4 centimeter is directly proportional to the mass number. And 19.2 is directly proportional to 16. This concept that I am substituting here, x is equal to 19.2 is directly proportional to 16. Divide one by the other. This divided by this. M divided by 16 is equal to 19.2 plus or minus 8.4 divided by 19.2. That is equal to 19.2, it's get cancelled. You are going to get 1 plus or minus 8.4 divided by 19.2. That is 7 divided by 16. Therefore, M is equal to how much? M is equal to 16 into 1 plus or minus 7 divided by 16. Therefore, M is equal to 16 plus or minus 7. That is equal to either the mass number is 23, 16 plus C, or the mass number is 16 minus 7, that is equal to 9. So these two are the answers. The mass number either it is 23 or it is 9. Okay. This is the next question. Taken from BETATRON. Okay. In a BETATRON, the maximum flux density of the orbit is 0.6 Tesla. The magnetizing coils are fed by 50 Hz AC. If the stable electron orbit radius is 5 meter, calculate the final energy and the average energy gained per revolution. This is the question. So again, we are supposed to think about that this particular problem taken from which particular concept? Taken from BETATRON. Whatever he has given, you are supposed to write it. Magnetic flux density is given. Magnetic flux density is given 0.6 Tesla. 50 Hertz is given. Frequency is given as 50 Hertz. Electron orbit radius is given. Orbit radius 5 meter. That is a radius, small r. How much is the final energy and how much is the average energy? Final energy is how much? Average energy is how much? So these two we are supposed to determine. Let us calculate first number of revolutions is how much? Number of revolutions. I will write that one as capital N is equal to C divided by 4 omega R, where omega is equal to 2 pi by capital T, or I can write 2 pi F, where T is the period, F is the frequency. So therefore omega is equal to 2 pi, frequency is 50, 100 pi. Radius is equal to 5 meter. C value, velocity of light in air or vacuum medium, 3 into 10 to the power 8 meter per second. With that velocity, it is revolving. So therefore, number of revolutions, capital N is equal to 3 into 10 to the power 8. Approximately it is revolving with the velocity of light. 4, 100, 3.14, 4 omega R into R. You will get the answer 0.0477 10 to the power 6. Now we can calculate final energy and average energy very easily. Final energy is how much? Final energy is equal to E is equal to BERC. Substitute here, get the answer. B value, magnetic flux 0.6, electron charge 1.6 10 to the power minus 19, radius is equal to 5, C value 3 into 10 to the power 8. You will get in terms of joules. Want to convert in the form of EV, divided by 1.6 10 to the power minus 19. You will get in terms of EV. If it is not divided by this, you will get in terms of joules. Divided by this, it is equal to EV. Therefore, final energy is given by 9 into 10 to the power 8 EV, or I can write 900 into 10 to the power 6 EV. Average energy we are supposed to calculate. Average energy gained per revolution is equal to how much? Average energy gained per revolution, that is equal to 900 into 10 to the power 6, that is the total energy, how much it is said to be existing, divided by number of revolutions. Already we got it now, number of revolutions 0.047, 0.0, number of revolutions 477 10 to the power 6, that is equal to 18867.92 so many EV. This is in terms of EV divided by the number of revolutions. You will get in terms of EV. Okay. Next problem. This is the problem taken from radioactivity. Radium has a half-life of 1500 years. In how many years 1 gram of radium it is losing 1 centigram? Question number 2 is reduces to 1 centigram. So you be careful about that. How much is the amount it is lost? How much is the amount it is reduced? So just we are supposed to answer these questions first. That means to say that first we are supposed to think about that. What do you mean by that first question and what do you mean by the second question? Okay. let me think about this concept first. Okay, first I will explain that, then I will take up this particular problem. Okay, we know about this particular formula. N is equal to n naught into e to the power minus lambda t. Okay, where n is how many number of atoms are left behind in the specimen. How many atoms are remained in the particular substance. How many number of atoms are remaining? How many number of atoms are left behind? This is initially how many number of atoms were present. Initially how many number of atoms are present, that is represented by n naught. N is how many number of atoms are intact. How many atoms are remaining, that is. How many, in the case of radioactivity, how many number of atoms are disintegrated number of atoms, it has no use. After disintegration, how many number of atoms are remaining, depending upon that radioactivity, it is go on, takes place. And where lambda is called by the name decay constant or disintegration constant. Decay constant or disintegration constant. Small t is the time interval. And we are having half-life period that is equal to capital T. You know that already. Capital T representing the half-life of a radioactive substance. Lambda representing the decay constant, or decay constant can also be written as disintegration constant. Capital T is the half-life. Small t is the total lifetime. Total time taken by the specimen. Then we are having one more formula here. Small t is equal to small n into capital T. If this is holds good, then the number of atoms, how many they are present, is given by n is equal to n naught divided by 2 to the power n. Okay, where t is the total time taken, capital T is the half-life, n is the number of half-lives, capital N is the number of atoms remaining, capital N naught is the number of atoms initially they are present, divided by 2 to the power n. Using the half-life concept, we are having all this formula, everything. Okay, based on this, we are supposed to solve the problem. So what is that problem that states? Let us take up this problem now. Okay, one by one now. Radium has a half-life of 1500 years. Half-life is